everyone. On this video, we will be going over equations of planes in space. Okay. So we know that from the previous video that we needed a point and a vector that's parallel to a line in order to find the equation of a line in space. Okay. Now we need the same thing for this equations of a plane, but we need a normal vector. Okay, and a normal vector is just another way to say perpendicular. Okay, so what we're going to do is we're going to draw our three-dimensional space. Okay, so we have our x, we have our y, and we have our z. Okay. So in that, we're going to draw kind of a three-dimensional plane. And let me move that up a little bit. Trying to get this to okay, so let's say bring that a little bit of a slant there. There we go. Okay, so just imagine that this is a plane, or if you want to visualize it, you can visualize it as a sheet of paper just floating in the air. Okay. All right. Okay, so let's say that on this plane we have a point P and a point Q sitting right on the plane. Okay, so this is point P, which will make equal our x0, y0, z0. Get those edges a little bit. There we go. And point Q, okay, we'll make that point X, Y, Z. All right. So now, on this plane, we're going to have a vector that's normal to the plane, or it's a right angle. And we'll call that vector N. And N will have that equal ABC. All right. Now, thing is, by these two points being on the same plane, these points are always orthogonal to this vector. Okay, so if we have, let's say, our vector here, and the vector going from the origin here, then this plane, as long as these 2 points are on it, will always be orthogonal. Now, if you remember, if you have 2 vectors, A and B, like I said, this is separate from this. I'm just kind of bringing up something. A and B, oh, didn't need to do that, are orthogonal, or in other words, normal, when their dot product is equal to 0. Let me separate that. There we go. Okay. So that means that our vector n, so to be normal, which is just another way to say 90-degree angle or orthogonal or perpendicular, our vector n and the dot product of the vector from P to Q has to equal 0. Okay, so this gives us our vector equation of a plane. Okay, now we don't have to work with that one. We're actually going to get this one and make it a little simpler to work with. Okay, so if we have the dot product of the end vector and the directed line segment from P to Q equals 0, we know that our normal vector is equal to ABC. Okay, so that's the dot product of A, B, C. And remember, from P to Q, we don't have a vector name for that one, so we're just going to actually calculate it. So x minus x0, y minus y0, and z minus z0. Okay, so we actually calculated our vector. All right, now if you remember, for your dot product, you get the first component. Oh, that's equals 0. Got that. First component times the first component plus the second component times the second component plus the third component times the third component. Okay, so that's A times x minus x0 plus B times y minus y0 plus C times z minus z0 is equal to 0. Okay, so if we go ahead and distribute A, B, and C, we end up with AX minus AX0 plus BY minus BY0 plus CZ minus CZ0 equals 0. Okay, so if we get just our X, Y, and Z and separate it from our X0, Y0, Z0, that will give us AX plus BY plus CZ minus AX0 minus BY0 minus CZ0 equals 0. And this portion here, we'll just say that's equal to the value D. Okay, so that will give us the equation AX plus BY plus CZ plus D equals 0, where D is equal to negative AX0 plus BY0 plus CZ0, and that gives you your formula for a linear equation of a plane. Okay, so the linear equation of a plane with a normal vector n, which is equal to A, B, and C. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and jump into our first example. right, so for example, let's say if we want to find an equation of the plane through the point 5, 3, 5, and with the normal vector 2I plus j minus k. All right. So we have our normal vector here, so we're just going to write that in regular vector form. So our n vector will be 2, 1, negative 1. And our point, 5, 3, 5. Okay, so we know for our normal vector, first component is A, second component is B, third component is C. And for our point, our x0, y0, z0. All right. So we know that x minus x0, plus b times y minus y0, plus c times z minus z0, plus d equals 0 is our equation. Okay, so we just go ahead and start plugging in values. So we have 2 times x minus 5 plus 1 times y minus 3 plus negative 1, or you can say minus 1, times z minus 5. There is no plus d value, so that's equal to 0. Okay, now just a little heads up, some textbooks will take this as your answer, but if it's not the answer they're looking for, you just go ahead and distribute our a, b, and c value. So we end up with 2x minus 10 plus y minus 3 plus z, oh, that should be minus 1. I make that a little clearer, almost made that error. Minus z plus 5 equals 0. Okay, so we get our x, y, and z term and put them together. So we have 2x plus y minus z minus 10 minus 3 plus 5. Okay, so this would actually be our d value. Okay, so we have 2x plus y minus z minus 8, if you add all that together, equals 0. Okay, so this is the equation of the plane through the point 5, 3, 5. That's perpendicular to the normal vector 2, 1, negative 1. Okay. Like I said, some textbooks will ask for that answer, but this is the answer that a lot of them will prefer. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go to our next example. Oops. All right, so for this example, what if we want to find an equation of the plane through the point 2, 4, 6 and parallel to the plane z equals x plus y. All right. So to start this one thing you have to notice is the wording in the question. Okay. You want to find the equation through this point and parallel to this plane. So, since the planes are parallel, they can have the same normal vector. Okay, so two different planes can have the same normal vector. Okay, so you're probably thinking to yourself, okay, how is that? Easy, they are parallel. So if you have this plane okay, so what if we have this plane here? What if we have a plane that's parallel to it? Okay, so what if this is our plane z equals x plus y? So whatever is perpendicular to this plane will be perpendicular to this plane. Okay, so you have two separate planes that can have the same perpendicular vector. Okay, don't be jealous of my fantastic artwork. Okay, so we know we have z equals x plus y. Okay, so if we subtract z on both sides, we end up with x plus y plus z equals 0. Okay, so if you remember, we have ax plus by plus cz plus d equals 0, and our normal vector has the components a, b, and c. Okay, so that means since this plane is parallel to the one we're trying to find, this can have the same normal vector. So that means a is equal to 1, b is equal to 1, and c is equal to 1. Oh, negative 1. Sorry about that. That should be minus. There we go. Because we did subtract z on both sides. Okay, so since their a, b, and c would be the same, that means that our normal vector will be 1, 1, and negative 1. Okay, so we found our normal vector, and they gave us our point, 2, 4, 6. So that's our x0, y0, z0. And this is our A, our B, and our C. Okay, so it's slowly starting to come together. Okay, so if we plug those into our formula, okay, so you have A times x minus x0 plus B times y minus y0 plus C times z minus z0. That's going to equal 0. Okay, so if we plug those values in, a is 1, b is 1, c is -1, x0 is 2, y0 is 4, z0 is 6. So we plug those in, we have 1 times x minus 2 plus 1 times y minus 4. Oh, that should be minus. Z is -1, so that's minus 1 times z minus 6 equals 0. And again, if we go ahead and distribute those, let me clean that up so there's no confusion. There we go. Actually, we're going to leave that there, and I'll show you why. Y minus 4 minus z minus 6 equals 0. Actually, this would be your answer, and I'll show you why. Let's say if we did go ahead and distribute this out. So we're just going to block this off for a second. So you have x minus 2 plus y minus 4 minus z minus 6 equals 0. Minus 2 minus 4, so that would be plus 6, is -6 plus 6 is 0. So we end up with x plus y minus z equals 0, which is the exact same as the second plane. So we can't give this answer as our new answer. Okay, so what this gave us one that is parallel. Remember, parallel dot product is just a scalar multiple. So that's why those two cancel out and we end up here. Okay, so for this problem, this will actually be your answer. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go to our next calculation, which is finding the angle between two planes. Okay. Now the thing is, we don't actually find the angle between the planes. Okay, that would be a little harder than we actually want to work. Okay, so instead of two planes, let's say if we have two planes here that are parallel, and we block that off. And let's say here we have two planes here that are perpendicular. Okay, so here, two planes that are parallel and two planes that are perpendicular. Okay, now I didn't put periods here because we're not done writing yet. Okay, so if you have two parallel planes, guess what? Will also be parallel. They're normal vectors. So the normal vector for this one will be parallel to that normal vector. Okay, so guess what here? If you have a normal vector to this plane, guess what? It will be perpendicular to the normal vector on this plane. So instead of trying to calculate the angle between two planes that can be infinite in size or approach infinity in size, we just find the angle between their two normal vectors. Okay, so two planes that are parallel will have parallel normal vectors. Okay, and two planes that are perpendicular will have perpendicular normal vectors. Okay, believe it or not, that's actually a whole lot easier to work with because you've done it already. Okay, so if you remember a few videos back, there you go. Cosine of theta, which is equal to the dot product of A and B divided by the magnitude of vectors A and B, can be used to find the angle between two vectors. Okay. Now, using that little reminder, we can see that the angle between the normal vectors is equal to the angle between the planes such that cosine theta is equal to the dot product of the first normal vector and the second normal vector divided by the magnitude of the first normal vector times the magnitude of the second normal vector. Okay, so we use the exact same formula to find the angle between two planes. Okay, now how do we use that? We can use it to find the angle, but we can also figure out that if they're perpendicular, then just like before, the dot product of the two vectors will equal 0. And if they're parallel, then the dot product of one will just be, not dot product, the multiple of one would just be equal to the other. Oops, sorry about that. Need to look up at the camera a little more. Okay, so if it's parallel, one vector is a scalar multiple of the other, and if it's perpendicular, their dot product will equal 0. You make that dot a little bigger. All right. So if you are still writing, feel free to press pause but we're going to go ahead and jump to our first example. All right. So for example, straighten up those papers. There we go. Determine whether the planes are parallel, perpendicular, or neither. Okay. Now, if it's neither, find the angle. Between them in degrees. All right, so the two planes are x plus 2y plus 2z equals 1, and 2x minus y plus 2z equals 1. Okay, so for this one, let's say for our normal vector number 1, we'll make that equal to a1, b1, and c number 1. And our normal vector number 2, we're going to make that equal to a2, b2, and c number 2. Okay, so if we get this equation, of course, we're going to subtract 1 from both sides. So we have x plus 2y plus 2z minus 1 equals 0. And we have for this one, 2x minus y plus 2z minus 1 equals 0. Okay, now remember, this is your A, B, and C. These are both in the form, and I'll put it in the little parentheses underneath it, ax plus by plus cz plus d equals 0. Okay, so that means for our first equation, our first normal vector is equal to a is equal to 1, b is equal to 2, c is equal to 2. So we have 1, 2, 2. And for our second normal vector, again, a is equal to 2, b is equal to negative 1, c is equal to 2. Okay, so we have 2, negative 1, and 2. Okay, so we were able to figure out our normal vectors just from the equations. All right. So now we can figure out whether or not they're parallel, perpendicular, or neither. Okay, so give it a little bit of separation there. Okay, so we can look at it just automatically and tell that it's not parallel, because neither one of these are multiples of the other. Okay, so if you multiply this one by 2, you won't get this vector. Okay, so they're not multiples of each other. If you multiply this by anything, you won't magically turn it into this vector. Okay, so they're not parallel, since vector n1 does not equal some multiple times vector n2. Okay, so that was a pretty easy thing to eyeball. Okay, now we have to find out if they're perpendicular. So we find the dot product of them. Okay, so that's just going to equal n1 is 1, 2, 2, and that's the dot product of our second vector, which is 2, negative 1, 2. Okay, so we know with the dot product, you get the multiply the first components plus the multiplication of the second plus the multiplication of the third. Okay, so we have 1 times 2 plus 2 times negative 1 plus 2 times 2 equals, we have 2 times 1, which is 2, plus we have 2 times negative 1, which is negative 2, plus we have 2 times 2, which is 4. We have 2 minus 2 plus 4, which is 4. Okay, so that means that the dot product of the first and second normal vectors equals 4, which does not equal 0. So if they don't equal 0, then we know it's not perpendicular. So it's not perpendicular and it's not parallel. Okay, so if it's not perpendicular and not parallel, we have to find out exactly what the angle is. Okay, so we know that. Give myself a little extra pencil lead here. Thought I had enough. All right. There we go. So we know that cosine of theta, bring that up a little bit, equals the dot product of our two end vectors and the magnitude of our vectors. Okay, so we already figured out the dot product up here. It's 4. So that kind of cut down on some of the work we have to do. So the magnitude of our first normal vector is the square root of each of the components added up. So we have square root of 1 squared plus 2 squared plus 2 squared times the magnitude of our second vector, which is the sum of each component squared. So we have times the square root of 2 squared plus negative 1 squared plus 2 squared. Okay, so that gives us 4 over the square root of 9. So we have 4 and 4 is 8 plus 1 is 9. Times, we have 4 and 1 is 9. So that gives us 4 over 9. Okay, so that cosine theta equals 4 over 9. Apply cosine inverse to both sides. We have theta is equal to cosine inverse of 4 over 9. And hopefully your calculators are set to degrees. Because if so, you would have 63.3 degrees as your answer. So that would be the angle between two planes, these two planes. All right. So if you are still writing, feel free to press pause. But we're going to look at one other thing before we call it a video. There we go. Move that down a little. Okay, and we're going to look at the distance between points, planes, and lines. Okay, so what if we have, draw this a little larger. Actually, let me bring that down just a smidgen so it's not running into the words. All right. So we're going to draw our plane. Okay, so we're going to go ahead and shade that in just a little bit. So that's our plane in three-dimensional space. You can kind of think of it as just a sheet of paper floating in the air. All right. So what we want to do is we want to find the distance between this plane and a point that's not on the plane that we will call point Q. Okay, so if we want to find the distance between these two, we know that if this point Q is over the plane, then at some point there's a spot on this paper that's just below it. So you can go over this whole paper or whole plane and you'll see a spot just below it. Okay, so that will be our normal vector. Okay, and we also know that on here, on this plane here, there is a point, some point P. Okay, that's sitting on the plane. Okay, now P will say that that has the point x0, y0, z0, and Q will say that has x1, y1, and z1. All right. So we know that our normal vector and our plane, they're right on the same line because they're on the same plane. Okay, so let's say our point Q is a little higher than our normal vector. Okay, and let's also say that we know that at some point we can create our directed line segment that leads us from point P to point Q. No matter where on the plane it is, we can guide it right to that point Q. Okay, so this is our end vector here. So our end vector, which just like before, we'll say that's A, B, C. What we want to do is we want to find what's the distance D from that plane to that point Q. Okay, so really everything we need to figure it out is right here. Okay, so let's say that our distance D, if you remember the scalar component, this is actually our scalar component of our vector or directed line segment P to Q onto our normal vector. Okay, so we can actually just use our scalar component formula. So D is equal to the dot product of our end vector and our vector from P to Q divided by the magnitude of our end vector. Okay. Now the thing is, this one's a little bit tricky, and I'll tell you why. If our point Q is below our plane, then you could have a negative value here. So this is the tricky part. In the numerator, you have the absolute value. So those lines are absolute value. But in the denominator, it is still the magnitude. Okay, because we're not trying to figure out whether this will all be positive anyway. We're not trying to figure out the negative or negative distance. We just want the overall distance. So in the numerator, the 2 bars are the absolute value. In the denominator, it's the magnitude. So that's the one tricky thing you have to remember, is that even though they look the same, they have 2 completely different uses. Okay, so once we continue on, you know that D is equal to, of course, we have our dot product. So you have the dot product of our normal vector, which is A, B, C, and our vector from P to Q, our directed line segment. So we don't have a vector, so we can create one. So you have x1 minus x0, y1 minus y0, and z1 minus z0. Okay, and that's all over our magnitude. You have the square root of a squared plus b squared plus c squared. Okay, so if we go ahead and get the dot product of our numerator, our distance is equal to, bring that up a little, the absolute value of a times x1 minus x0 plus b times y1 minus y0 plus c times z1 minus z0 all over the square root of a squared plus b squared plus c squared, or, bring that up a little, we have D equals the absolute value of a x1 plus b y1 plus c z1 plus d all over the square root of a squared plus b squared plus c squared. So really you can use either formula, either one of those formulas. Okay, so to cut back on the confusion here between the absolute value and magnitude, that's why it's shown as just the square root of each term squared. Okay, so we know that this is where Q, x1, y1, z1 is a point not on the plane. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go to our first example. That's the end of that there. All right, so for example, what if we wanted to find the distance from the point -6, 3, 5 to the plane x minus 2y minus 4z equals 8. All right, so to start this one, we have our point -6, 3, 5. Remember, our point Q isn't on the plane, so that's our Q. So this would be our x1, y1, and z1. And our x minus 2y minus 4z. Remember, we're going to bring everything to the left, so we subtract h on both sides, equals 0. Okay, so if we bring that over, remember it's in the form ax plus by plus cz plus d equals 0. So that means our a is equal to 1, our b is equal to -2, our c is equal to -4, and our d is equal to -8. Okay, so we have everything we need to just plug right into the formula. Okay, so since we don't have an x0, y0, and z0, the formula we're going to use is ax1 plus by1 plus cz1 plus d all over the square root of a squared plus b squared plus c squared. Oh, clean up that square there a little bit. All right, so if we go ahead and just plug everything in, our distance is equal to the absolute value of 1 times -6 plus -2 times 3 plus -4 times 5 plus -8 all over the square root of 1 squared plus -2 squared plus -4 squared. Okay, so that's going to equal the absolute value of -40 over square root of 21, which is just 40 over the square root of 21. Okay, so it's not too horrible. Okay, so if you're still writing, feel free to press pause, but we're going to go ahead and go to our next example. All right, so for example, what if we wanted to find the distance between the given parallel planes? Okay, so you have 6z equals 4y minus 2x, and you have 9z equals 1 minus 3x plus 6y. All right. So let's say for 6z equals 4y minus 2x, we'll say that's our first plane. And let's say for 9z equals 1 minus 3x plus 6y, that's our second plane. Okay, so we can kind of distinguish one from the other. Okay, so if you think about it this way, let's say, just to kind of give you a way to visualize it. Okay, so they're two parallel planes. So if we have this plane and we have this plane and they're both parallel to each other, then that means if we have our second plane here, we don't have to find the distance between both planes. We just have to find the distance between this plane and some dot on that plane. Okay, so that dot is all we need. So we find the distance between this plane and that dot, we found the distance between both planes. Okay, So what we're going to do is we're going to bring everything over on this one. So we have 2x minus 4y plus 6z equals 0. And this one we're going to do the same thing. So we have 3x minus 6y plus 9z minus 1 equals 0. Okay, so all we did was bring all of these variables to one side, or everything really to one side. Okay, so for this one, the first plane, we have to find a dot. We have to find an x, a y, and a z we can plug in that would make it equal 0. Okay? And you know what I always say, keep it simple. I make more work for yourself. So we'll just let x equals 0, y equals 0, and z equals 0. If x, y, and z are all 0, you have 0 equals 0, which would make this true. Okay, so that means, 0, 0, 0 is a point on the first plane. So bring that in down. There we go. All right, so we have our point on the first plane, and we have our second plane. So now all we have to do is find the distance. Bring this up a little bit. Between Q of 0, 0, 0, and the second plane. Okay, so to do that, remember, Q is the point off of the plane. So that would be our x1, y1, z1. And our second plane, 3x minus 6y plus 9z minus 1 equals 0. Remember just how we did before. We know that a is equal to 3, b is equal to negative 6, c is equal to 9, and d is equal to negative 1. All right. So we just go ahead and plug that right into our formula. Okay, so we know that the distance is equal to ax1 plus by1 plus cz1 plus d all over the square root of a squared plus b squared plus c squared. And let me kind of separate that a little bit. Okay, so that means our distance is equal to the absolute value of 3 times 0 plus negative 6 times 0 plus 9 times 0 plus d, which is negative 1, all over the square root of 3 squared plus negative 6 squared plus 9 squared. Okay, so that's going to equal, since all these are just 0, that's why I said pick 0, because it made all of that so easy. So the absolute value of negative 1 over square root of 126, which is just 1 over square root of 126. And actually that can be simplified. So we're going to make that 1 over square root of 9 times 14. Since 9 times 14 is 126. Okay, so that 9 can be factored out, so that would give us 3 times square root of 14. Okay, so that's 1 over 3 times the square root of 14 as your distance. All right. Okay, so hopefully these explanations made sense to you, and I will see you on the next video.